Okay, 5.5, integration by substitution. So now we're kind of getting a more general way of integrating that doesn't just rely on basic integral rules. So recall before our integral rules, we noted that if I know the derivative with respect to x of something like sine of x is equal to cosine x, then I can say the integral of cosine of x dx is equal to sine of x, sort of, right, plus c. We want to sort of take this up a notch. So for instance, the derivative of x, the derivative of something like, let's say, sine of x squared. Okay, so we have a composite in here. That's equal to what? Well, it's cosine of x squared, and then you have to multiply by the derivative of the x squared. It's the chain rule, right? So it's times 2x. In other words, this is equal to 2x cosine of x squared. So the corresponding rule then, the integral of 2x cosine of x squared dx is equal to, well, sine of x squared plus c. Okay, so we want a method that will allow us to pull this off, because in general it's maybe not entirely clear that you have kind of the result of a chain rule over here. Okay, it's not as clear as these, because you're supposed to have these memorized, you know, and so they hope that if you see the integral of something that you have memorized as a derivative, you'll be able to do the reverse process. Here, you don't really have these memorized. You just kind of have a process for doing it. So recognizing this as this, oh, that's not as easy. So we've developed these methods that will allow you to pull this off. And the key to it is kind of recognizing a function like the x squared here, and then noting its derivative is sitting also over here. It's just the problem is it's not always going to be so nice. For example, you may be asked to find the integral of x cosine of x squared. And in that case, certainly you have this x squared and then this thing again. They're kind of derivatives of each other, right? The derivative of 2x is kind of x. There's really a constant there. So what you have to do is what the book kind of does, is kind of levels out the playing field. So this integral is the same as 1/2 times 2x cosine of x squared dx. Okay, so 1/2 times 2 will give you this, but I know the antiderivative of this thing right here. Right, I know that's the sine of x squared, so this will equal then 1/2 times the sine of x squared dx, plus c, sorry. So the book advocates this kind of leveling method. So if you're missing a constant, you can just multiply in by its inverse, and then evaluate this thing, because you'll know the antiderivative. What I advocate is kind of what's called a U substitution, which I think is the way to go. All right, so let's get in there and take a look at it in all of its glory. So we'll start with number 2. And we have, well, what is this? Let me title it. This is 5.5. Did I already do that? Yeah, already. 5.5, integration by substitution. And we're doing U substitutions. Okay, so section 1 in my notes. U substitution. Okie dokie then. Let's look at number 2. So we have the integral of x squared times the square root of x cubed plus 1 dx. So I see that x cubed plus 1, its derivative is a lot like x squared, right? So that's going to be my U substitution. I'm going to let U equal the x cubed plus 1 and then I take its derivative, and I do the differential form of the derivative. Okay, so I'm not going to write y prime equals 3x squared. I'm going to write du equals 3x squared dx. Okay. Then I work it as a substitution. I need an expression for dx to substitute everything into here and turn it into an integral in terms of u. So I can solve for dx, and that'll be du all over 3x squared. Okay, so I use this information to turn this into an integral in terms of u. So x cubed plus 1 is u, and then dx is du all over 3x squared. If I consider this as just a bunch of factors, I note that this x squared here and this x squared here will divide out. On top of that, I have a fraction of 1/3 that I can factor out the front. So it'll be 1/3 integral of the square root of u du at the end of the day. So what you've done is transform this into an integral that you will know how to do from your basic integral rules. You could do a power rule here. This is 1/3 integral of u to the 1/2 du. So I'll have 1/3 times u to the 1/2 plus 1 is 3/2 times 2/3 plus c. And then simplify, so 2/9 times u is x cubed plus 1, so I back substitute to the 3/2 and then plus c. And then that's it. Okay, so let's just pound out a whole bunch of these. Number 6, we have the integral of x squared minus 9 cubed times 2x dx. This one's a little easier because the actual derivative of the u sub will be sitting right here. Okay. But let's do it the way I'm trying to teach you. So u is equal to this stuff, because I know the derivative is sitting right here. So x squared minus 9. Du will be 2x dx. In other words, dx is du all over 2x. Okay. So I replace the x squared minus 9. I'll end up with the integral of u cubed times 2x times dx, which is now du over 2x. So if you do a good u sub, and sometimes you have to kind of guess your u sub, and if it doesn't work, you have to try something else. But if you guess it right, all of the x material will go away. And in this case, we just end up with u cubed du. And then integrate that, you get u to the 4th over 4 plus c. And then back substituting x squared minus 9 to the 4th all over 4 plus c. Let's keep going. So number 10, I have the integral of x squared times 6 minus x cubed to the 5th dx. Okay, so note the derivative of this is sitting right here, 6 minus x cubed. I'm going to let that be my u sub. And then du will be negative 3x squared dx. And you can solve for dx to do your sub. So du all over negative 3x squared. Okay. So this will be the integral of x squared times, I'm replacing this with u, so I'll have u to the 5th, and then I'm replacing dx with du all over negative 3x squared. Okay, so the constant I can pull out is a negative 1/3. The x squares divide out, and I'll have u to the 5th du. So you end up with negative 1/3. U to the 6 over 6, or in other words, 1/6 times u to the 6. And then you have to back sub, so this will be negative 1/18 times 6 minus x cubed to the 6 plus c. Let's try 14. We have the integral of t cubed times the square root of 2t to the 4th plus 3 dt. Okay, so I'm going to, I note that the derivative of this stuff is like this guy right here. So that's stuff. I'm going to make my u sub. So du is 8t cubed dt. And then dt will be du all over 8t cubed. So I replace the stuff inside the square root with u, and then dt is now du all over 8t cubed. So the t cubes will cancel out. I have a constant of 1/8. Square root of u is the same as u to the 1/2 du. So this will be 1/8 times u now to the 3/2 times 2/3 plus c. So 2 over 8 is the same as 1 over 4. So I get 1/12 times u, which is 2t to the 4th plus 3 to the 3/2 plus c. Two more, and then we'll talk about definite integrals. So these have all been indefinite integrals. We're just finding antiderivatives and slapping on a plus c. Okay, so it looks like the derivative of 1 plus x to the 4th is kind of x cubed, right? So we'll let u be 1 plus x to the 4th. Du is 4x cubed dx. So my dx will be du all over 4x cubed. So this will be the integral of x cubed all over u squared times du all over 4x cubed. The x cubes divide out. I can factor out 1/4. And I have the integral 1 over u squared is u to the negative 2. Add 1 to the old exponent, so I have negative 1. And then divide by negative 1 is the same as multiplying by negative 1. So I get negative 1 all over 4 times u to the 1. So u is 1 plus x to the 4. And 1 plus c. One more. 26, the integral of x all over the cube root of 5x squared. So I can let u be the 5x squared, and then du will be 10x dx. And so dx will be du over 10x. So I have x all over the cube root of u times du all over 10x. The x's cancel. I have a factor of 1/10. And then the integral of 1 over cube root of u is the same as u to the negative 1/3 du. I have 1/10. U to the negative 1/3 plus 3/3 is u to the 2/3 times 3/2. And simplifying with the back sub, I have 3/20 times 5x squared to the 2/3 plus c. Okay, so now I want to do some definite integrals, and there's two methods. You can change the limits, and then you don't have to do that back sub at the end. Okay, so let's look at that. So this is 72. I have the integral from 0 to 1 of x times the square root of 1 minus x squared dx. Okay, so I'll do my u sub, and looks like the 1 minus x squared will be a good guess. So du is negative 2x dx, and dx is negative du over 2x. Okay, now I'm going to tack on some change of bounds. So this is a function of x, And really what you're thinking of is the limits go from x equals 0 to x equals 1. You can always kind of embed that in there if you wanted. But we want to go from u equals something to u equals something. So I plug the x into this formula. So I'm going from u of 0, which is 1 minus 0, which is 1, to u of the upper limit, which is 1. So in that case, 1 minus 1 squared, which is 0. So now my integral is going from 1 to 0. We'll have x times the square root of u times dx, which is negative du over 2x. The x's cancel. I could factor out a constant of negative 1/2 times the integral of u to the 1/2 du from 1 to 0. Find its antiderivative, so negative 1/2 u to the 1/2 plus 2/2 is u to the 3/2 times 2/3. And I need to evaluate from 1 to 0. So I'm getting negative 1/3, and then I'm plugging in 0, and 0 to the 3/2, minus plug in 1, so you get 1 to the 3/2. 0 to the 3/2 is 0, so I just get minus 1. So negative 1/3 times minus 1 is 1/3. Let's try one more of those, just so we get the idea. So 73, I'm integrating from 0 to 4 of 1 all over the square root of 2x plus 1 dx. So in this case, I need a u sub for this material down here, right? So I'm letting u equal 2x plus 1, and then du equals 2 dx, and then dx equals du over 2. Okay. And then I need to change my bounds. So using this formula, I know u of 0 is equal to 1, and then u of 4 is equal to 9. So my integral becomes the integral from 1 to 9 of 1 all over the square root of u times dx, which is now du over 2. I have to factor out 1/2, so I'll get 1/2 integral of u to the negative 1/2 du. And then that's 1/2 times u to the negative 1/2 plus 1 is 1/2 times the reciprocal of 1/2, and I'm evaluating from 1 to 9. Of course, that will just be 2 times 1/2 is 1, so I'll just have u to the 1/2. So plug 9 into that, you get 9 to the 1/2. And then minus plugging 1 into that, you get 1 to the 1/2. So 9 to the 1/2 is 3, minus 1 to the 1/2 is 1. In other words, we get 2. Okay, so you can always pull that trick. If you don't like that, you can always just back substitute and then evaluate the integral as you normally would. So let's look at the integral of 1 all over 5 minus 2x dx from, I don't know, negative 3 to or rather 3 to, sorry, it's taking me a second, I'm going to make this up, 3 to, I don't know, 4. Okay, so my u sub I have to do for the denominator, 5 minus 2x, and then du is going to be negative 2 dx. So dx is negative du over 2. Okay, and what you do is just drop the limits and work the antiderivative. So I have 1 all over u times negative du over 2. So this is process 2. You're going to have to do a back sub at the end. Okay, so this integral, I can bring out the negative 1/2, and I have the integral of 1 over u du, okay, which we know is a natural log integral. So this is negative 1/2 ln of the absolute value of u. And we have to evaluate. But before we can evaluate, we need the back sub. So I just back sub negative 1/2 ln of the absolute value of 5 minus 2x. And now you can evaluate from 3 to the 4. Okay, so you have to get it back in terms of x if you want to use the original limits. Okay, so it's negative 1/2 ln of the absolute value of 5 minus 8, which is negative 3, minus negative 1/2 times ln of the absolute value of 5 minus 6, which is negative 1. So this will be negative 1/2 ln 3 plus 1/2 ln of 1, which is 0. So it's going to end up being negative 1/2 ln 3. Let's try one more of those. We'll take one from the book this time. This is 73. No, it's not 73. Let's do 77. So 77. The integral of e to the... No, let's do 79. Sorry. These are just not very interesting. 79. Let's try the integral of e to the 3 over x all over x squared dx. And we're going from 1 to 3. And we're using the back sub method for definite integrals. Okay. So my u, it may not be obvious in this case, but the u should be this guy, the 3 over x, because its derivative is kind of this guy. It's actually negative 3 over x squared. So we'll let u be 3 over x, which you'd rather write it 3x to the negative 1. Then du is negative 3x to the negative 2 dx. So dx is going to be equal to x squared, negative x squared all over 3 du. Okay, so I do my substitutions. I'm going to drop the limits. I'll have e to the u all over x squared times x negative x squared all over 3 du. The x squares cancel. I can factor out a constant of negative 1/3, and then I have the integral of e to the u du. So it's negative 1/3 e to the u. I have to evaluate, but I have to back sub first. So negative 1/3 e to the 3 over x from 1 to 3. And so I get negative 1/3 times e to the 3 over 3, which is 1, minus e to the 3 over 1, which looks like that. Okay? And then you go to your calculator and get an approximation for that. Okay, some clever things about these integrals. If they are even or odd, you can kind of figure out the integral quickly or simply. So first off, the function has to be integrable, but if the function f is even, you can kind of split it in half and just multiply it by 2. So remember, if a function is even, it's symmetric about the y-axis. So if you find the area under here, you basically have already found then the area under here. In other words, to find the total area, you just need to find the area under here and multiply it by 2. So just find half the area and multiply it by 2. So if f is even, the integral from negative a to positive a of f of x dx is going to be 2 times the integral from 0 to a of f of x dx. Okay, then likewise, too, if f is odd, then the area, the curve will look something like this. So the area underneath the curve here and the area underneath the curve here will be opposites of each other, because this will be negative area, this will be positive area, and then when you find this area and add it to this area, it'll be 0. So the integral, and this doesn't look like it, but it's an a. It's going from negative a to a. If f is odd, then the integral from negative a to a of f of x dx will just be equal to 0. Okay, so a simple example of that the integral of x times the square root of 9 minus x squared dx from -1 to 1. Okay, so you may be tempted to do a u sub for this material here, but if you note the function f of x equaling x times the square root of 9 minus x squared, you do the test for oddness, which says if f of negative x equals negative f of x, then it's odd. So remember these rules. F of negative x equaling f of x means it's even. F of negative x equaling negative f of x means it's odd. Okay. So if you plug negative x in here, you get negative x square root of 9 minus negative x squared, which of course equals negative x times the square root of 9 minus x squared, which of course is negative f of x, which implies it's odd. You need not do the u substitution because automatically then that implies that thing is equal to 0. Okay? The oddness and the fact that we're looking at an integral that's symmetric about the y-axis indicates that the integral is actually equal to 0. So you can simplify your calculations dramatically if you take advantage of some of these little laws. Okay, thanks for watching. Bye.